Okay. Yeah, you'll come right after. Good. So our next speaker will be Marc, who's going to talk about Euclid.
Great. Thank you so much. Always a pleasure to be back here. Also, I must say the room feels a bit empty without Avishai in that corner asking questions, so we miss you. My talk today was going to be a bit different, although I'm usually talk here about machine learning and call it, by default, put it in the program. I thought I would change the topic and talk a little bit about Euclid, which is a big thing that has been happening this year and kept me busy. And so I'm going to put my European hat and show you a little bit of what Euclid has done for galaxies and plans to do. So a quick recap of what Euclid is, although probably you all know. It's a small telescope, space telescope, 1.2 meters, slightly smaller than Hubble. It has mainly two instruments, VIS, which is an imager with a large field of view, half a square degrees, and an infrared imager with 3 filters, which does also spectroscopy, so the instrument. And the planning for the mission, it was launched in July 2023. It's close to the JWST in the Lagrange point. The survey duration is expected to be around 6 years. And it's a cosmology mission, so the plan is to observe 1/3 of the visible sky, so 15,000 square degrees at very high resolution. So the main goals are cosmology, but it's a very large legacy for galaxy evolution in terms of imaging. So just a few notes. So as I just said, there's two main surveys. One that we call wide survey, which is essentially covering 15,000 square degrees. And then there's a deep survey, which is much smaller, around 50. And then which goes 2 magnitudes deeper. So this is concentrated in 3 deep fields, which I'll go back to that. And probably, so this is the most interesting part for galaxy formation. At the wide depth, we reach a depth of 24.5 in the optical at 10 sigma. And you can see there the wavelength ranges. So one particular thing of Euclid is that in the optical, it has only one broadband filter, which is essentially 2 HST filters together. Right, so this is the plan for the survey as time goes by. So we're planning to cover mostly 1/3 of the sky. And so these yellow things are 3 deep fields I just told you about: Euclid Deep Field North, South, and Fornax. And so these patches on the sky will be 2 magnitudes deeper. And this is essentially what has been released in March, what we call the quick data release or Q1 data release. So it's a first pass, so at the wide depth on the Euclid deep fields. So what's in the Q1 data release? So as I said, it's one pass on the deep fields. Is around 63 degrees square with all the instruments and also including all what we call X data, which is all the ground-based follow-up. And so essentially, it's at the wide depth, so it gives you a flavor over what the wide survey would be. So the next data release, what with the big data release that we call DR1, is coming publicly next year. So in the fall 2026, it will be around 2,000 square degrees. So particularly for Q1, there's no cosmology, so cosmology will happen in DR1. And then, so this has been so the result of Q1, which was released in March, has been 7 technical papers describing the data that are out there, and around 30 scientific papers, mostly focused on galaxies because there's no cosmology, that appeared on arXiv altogether in March 2025. So just want to make a point because I always talk about AI, so that 60% of these papers make heavy use of artificial intelligence. So this gives you also a flavor of what's coming with these large data surveys and also with Rubin in terms of data processing. So just a flyby on this field, so the projector doesn't do justice to it, but this is the Euclid Deep Field South, and you can see the image quality, which is very comparable to Hubble, with around 0.15 arc seconds in PSF. All right. So just a flyby on some of the things, capabilities of Euclid. So Q1 has essentially been a showcase of what Euclid can do. And so I'll be just flying by some of the things. And so one big thing that Euclid is opening is a new parameter space for looking for nearby dwarf galaxies that are important for constraining dark matter models, for example. And the dark matter structure, you can put constraints on dark matter nature by these dwarf galaxies. Euclid is observing plenty of them. So just on the Q1, we detected like around 10,000. DR1 is expected to detect around 400 million dwarf galaxies, and overall 2 million, billion on the white surface. So you can get some diversity of morphologies. This is what the high resolution does for Euclid. So you can get not only the detection of dwarfs, but look at the different morphologies. Here you don't see them, but there are also some nice low surface brightness galaxies that are detected. So a bunch of science that can be done with this. Right. So close to my heart is galaxy morphology, and I've been trying to push this forward for the past years. So I think we have managed to provide, I think, the first implementation of deep neural networks directly in a space mission, so which also translates, it's a translation of how AI is becoming a mature technology for astro. So, and so basically we do on-the-fly morphological classification of all galaxies observed in Q1. This is an example of different types of the morphology diversity that you get. So Mike Walmsley has put together a nice way of visualizing this, in which you can just browse the catalog that is now public, and then you can look at the different morphologies and select based on quite detailed morphology. You can also detect artifacts and this kind of stuff. So this is publicly available. Just feel free to go and play with the data. One thing that we looked at with this catalog, the things that you can start doing on the fly just with the Euclid catalog that is available is, for example, looking at detailed morphologies. I led a paper looking at bars, because bars have become again a hot topic with JWST results. I didn't know that it was that complicated. But essentially, this is just, again, a showcase in which you can look at the bar fraction of galaxies as a function of redshift. So it's not JWST, it doesn't go to redshift 5. It's very nearby universe. But you can see, compared to HST, these are all these data points. There's also some JWST points there. We're more or less in the same ballpark, but essentially, Euclid is now dominated by systematics. And this is, again, a big thing of what's going to happen with these large surveys. So we need to start taking care of systematics much closer. Just a comment on this is not Euclid, this is JWST. I mentioned bars are, again, a topic because they can tell you about the origin of disks, and JWST detects bars down to redshift 4 or 5. And you can start using these stellar bars. People have been using these to put constraints on the emergence of disks. And this is some discussion we had yesterday, but if you use bars to constrain, you get something that above 10 to the 10 stellar disk starts to emerge or be dominant in the start forming main sequence around redshift 1.52. I think roughly in agreement with what we heard yesterday. Good. You also get from Euclid on the fly, we provided all structural measurements, so you can look at your favorite scaling relations with now way more statistics than in HST. Everything looks normal, but again, I think I liked what you can do with Euclid is really go, and you have plenty of statistics there where HST barely sees some objects at the high mass end, where you have plenty of objects that you can explore, and so you can put way more constraints, better constraints on the very massive end of the scaling laws and mass functions, which I'm not showing here. All right. Machine learning has also been used to detect mergers. Again, this is the main thing that Euclid can do because of the wide area is to focus on rare objects. And so mergers, we increase a lot the statistics. And this is a machine learning model trained on simulations, actually. cosmological simulations, and then combined with another machine learning model to look for AGN luminosity or detect AGNs. Antonio has been correlating the merger fraction with the AGN luminosity, finding very tight relations, which needs to be checked again. But this is the kind of statistics that you can start doing with Euclid with the numbers we're reaching. A big thing that Euclid is offering as well is, again, the main thing is, again, looking at weird or rare objects. Strong lensing is an example of this, and Euclid is opening a new parameter space on that regime, again, to put constraints on the nature of dark matter. So these are images from the, not Euclid, so from the HSC legacy survey of potential lens candidates, and this is how they are looking Euclid. So it doesn't, again, the projector doesn't does justice, but you can see the difference and really, how you can start seeing the structure of lenses there. So Euclid is opening a new parameter space in terms of strong lens detection. So typically with ground-based facilities, you cannot probe things below 1 arc second in Einstein radius because of the seeing limited imaging. Euclid is opening this parameter space quite nicely and now going into the peak of the strong lensing distribution. So the number of lenses that we expect to detect in Q1, we already around 100 lenses. We plan to reach 100,000 lenses for statistical analysis. Again, this is opening a new regime. Right. Another thing that the wide area of Euclid allows you to do for galaxy formation is looking at the environment, which much better statistics that you can do with HST. And again, these are all showcases, so preliminary work. Claude has been working trying to use disperse to reconstruct the cosmic web in a small tomographic bin of redshift space to show how we can do. So this is again very preliminary because it's based on photometric redshifts alone. We are not using the spec Zs yet, but it gives you a potential of what you can do, reconstruct the cosmic web at large scales. And this is an example of the cosmic web reconstruction and a zoom in on the Euclid image. You see that there's a node there where the cluster is lying. And Clotilde has been looking at statistics with filaments. So again, this is very preliminary, but how the morphology parameterized with the Sersic index correlates with the distance to filaments, and also looking at alignments of galaxies with filaments, finding that already a known result, but that early type galaxies tend to be aligned with the filament. So these again things that you can do with Euclid much better once you get larger field of views and better constraints on redshifts. All right, Euclid, I think last thing I'm going to mention, Euclid has also been looking at LRDs because it's completely different parameter space than JWST, but because we know that the number densities, or I think that's the main trend or thought that the number densities of LRDs are decreasing with redshift. So they are pretty rare in a low redshift. So pencil beam surveys like JWST are having harder time to find them. So with Euclid, you can try to find them in wider areas. So this is tricky. Again, this is again preliminary work because Laura has been looking for them based on the shape of the SCD, combining with ground facilities. But she found a bunch of candidates at a lower redshift, so completely complementary with the JWST finds. Not all of them probably are correct. They need to be followed up. But it shows, again, the potential of finding these objects at lower redshifts. She's been compiling UV luminosity functions, comparing them to high redshift of JWST. Here, sorry. So you see there's a clear decrease, but maybe not that steep as JWST results show. So it's something to follow up. All right, I will finish with an AI note, and Euclid also can help to that, also in general big data astronomy. So I always try to bring you here what the news from the AI world. And one thing that is happening in AI is that we are moving into another regime, which what we call foundation models. And it's more or less based on the success of GPT-like models, in the sense that instead of training one specific model to do galaxy morphology, or one specific model to do some particular thing, we are trying to feed a big foundation model with all the data we have without any specific purpose. And this model learn general tasks and be used for many different tasks. So what does that mean for Astro is that hopefully in the near future, you never will have to train a neural network from scratch, because you will download big neural networks that have been trained. You don't need models. GPT is just trained on massive text. You can translate these to big surveys and train on all the data that is available out there. And integrates all data, which is important. You can train these models with what we call multimodalities, so going from spectra to images, time series, trying to integrate multiple surveys together, and really have a representation space, an embedding space here that understands all the data we have. And you can also ideally plug in their simulations and try to connect both. So this is still preliminary. We are built our own model, which we call AstroPT, not very original. There are many in the market there. But the idea is, again, to try to use the LLM architecture, but feeding, instead of tokens of text, feeding tokens of images and other multimodalities, in that case, SEDs and images. So this is a visualization of a multimodal model that combines spectral energy distributions and images on Euclid data. And you know why Euclid? Because you need large data sets to train these models. This is completely self-supervised, but you need lots of data. And so you can start seeing that these models, without being trained for any specific purpose, they have emerging behaviors. And when you look at this representation space, and now only plotted here in 2 dimensions, color-coded by, for example, morphology and redshift, and depending on how many modalities you add, you can add only visible, you can add visible and infrared, visible and infrared plus ground-based SEDs. And these models, they don't know anything about morphology, they don't know anything about redshifts, but nevertheless, they have fine correlations with these parameters. And then you can find that as you add more information in multi-wavelength, you get more sensitive to redshifts. And so this means that these embeddings are informative. And so then you can use, instead of training a new model, you can use this and infer morphology and redshifts out of the box. So this is probably going on. We'll see more in the next few years, I think, as a standard way of doing ML for science. All right, so I'll stop here. So my takeaways are that Euclid Q1, I think, demonstrates that the revolutionary capabilities of Euclid for high-resolution imaging. Before Roman arrives, it's a lasting legacy for high resolution, I think, in the optical and infrared. There's many potential for galaxy formation. Q1 papers are just a showcase, but we can go from very local universe like dwarfs to large-scale environment, probing the impact of AGNs and providing statistical relations that can be compared to models accurately. AI is playing a big fundamental role in analyzing these surveys, and I think we're going to see the same thing with Rubin coming in. And stay tuned for DR1, where cosmology will happen. Thank you.
Do we have a question while Martin sets up?
Very cool talk. I have a question about the density fields for the cosmic web. How can you speak to how uncertain the density field reconstructions are from photometric redshifts with Euclid?
So they are uncertain, for sure. What Clotilde has been doing is integrating the uncertainty, the full PDF of the photo Z in the reconstruction. So she's sampling the density field based on the photo Z uncertainties. So what you see there is a median of the samples. So it's uncertain, but we try to integrate the uncertainty into the reconstruction. Disperse. Ah, okay. So, yeah.
Okay, one more real quick from David.
Would there be any multiple exposures for the wide field or only for the deep fields?
Only for the deep
Multiple
fields.
time.
Only for the deep fields.
Only for deep.
Okay, let's thank